So in this class, we're going to do a set of functions called moment generating functions. So before, we've already seen for both discrete and continuous random variables. Let's see, discrete and continuous random variables. We have seen the concept of distribution functions. So we've seen distribution functions. So these functions determine the distribution of the random variable. So in this lecture, we will discuss what's called these moment generating functions. These also characterize what's called the moments of the random variable, and those in turn will determine the distribution of the random variable. So it's something similar to what distribution functions do for discrete and continuous random variables. We will develop another characterizing concept of distribution via moment generating functions, and they also serve as good tools, these moment generating functions. So let me first define what's a moment, then we'll start with that. Let's see. So first definition is, so let's say what a moment is. So moment of a random variable So the moment is the following. So suppose x is a random variable. Let x be a random variable. Then take a positive integer k. Okay, let x be a positive integer k. Let x be a positive integer k. Let k be a positive integer. Then the moment of x is defined as a of x to the k. So the quantity so I'll call it m sub k. It depends on x. So it's expected value of x to the power k. So this is called the moment of k, is known as the kth moment of x. Of course, now this kth moment may or may not exist, so we'll just keep this in mind as before. So as before, the moment may or may not exist. Okay, the moment, because you will need the expectation to exist, so the moment may or may not exist. Okay, that's this one. So this is expectation right here. So this expectation may or may not exist depending on how this either the integral or the series converged, right? So now we had discussed before this. What have we seen before? We have seen before the first moment. Let's recall. So let's recall a little bit. So recall, before we've already seen the following. We've called it the mean or the first moment. So that's just e of x power 1, which is the same as e of x. So this quantity we have seen. We've also seen the second moment in another context. We've seen it in variance. So we know that the variance of x is e of x minus e of x squared minus e of x the whole squared, right? And so let me write this down properly. So e of x squared minus e of x the whole squared. So this essentially is the second moment. So we've seen this used before, and we're just sort of giving it a special name now. But again, here it's true for every k. This is for every k. K is a positive integer, so k equal to, so your k can be equal to 1, 2, 3, and so on and so forth. So there's one interesting fact about moment generating function, which I will not prove, but you can see the proof in the book. In the book, it's theorem 6.3.2 in the book. This book is the one that's available on our website, and it's the probability examples using R. So the one interesting fact about moments is the following. If you have a moment of order k, then moment of order j for j less than k is always well defined. So let's write that fact down. So suppose e of x to the k is finite for some k positive, right? Then for j less than k, e of x to the j is also finite. Right, so that's like for all integers less than k, e of x to j. So this proof I will not show, but it's a very useful thing to do. So if you have moments of one order, then everybody else below it is also finite. So in some cases, the moments serve to complete discrete distribution. In some cases, they will not. We will try to see in what cases they will describe the distribution completely. So here's the next definition, which I'd like to do. It's called the moment generating function. So let me write this down. So here, everything is blue. Let's write on blue. Moment generating function. So here what I'll do is I'll define a set D. Let D be the set. Let D be the set of all t in R such that the expected value of e to the tx is finite. Okay. So again, let's just let's go a little bit step by step. So let's start with a random variable x. Let x be a random variable. Let D be defined as this set where a set of all t for e of tx is finite. Then the function m from D to the real line or to the positive real line given by m of t is just expected value of e to the tx is called the moment generating function. Okay. So as of now, this function is a name. It's called moment generating function. The function is defined by m of t is expected value of e to the tx. Okay. We'll now try to understand why this name is given and why it is related to the moments. The first thing to observe is that this is a special type of expectation. It's expectation of an exponential function, e to the tx. Right? That's one thing we observe. Again, I'm also going to go and sort of state that we are after this following idea that we think that moments are as good as distribution functions. So if you know all the moments, then you know a lot about the distribution of a variable. This is something that that's the motivation for all this. Okay, so the motivation for all this is that in some cases, so why this name is a question. Why this name for m? We'll come to that in a second. And next thing is the motivation for all this is that in some cases, if m sub k is known for all k positive, then the distribution of x is determined. Okay. Then the distribution of x is determined. Very nice. So that's one primary motivation for understanding moments. And why is this function important? So I'll state a certain fact. It's quite easy to do. But before that, let's do a couple of examples before we do this name. Let's do a bunch of examples, understanding what the moment generating function looks like. Okay, so let's do an example. So let's say x is Bernoulli. Okay, so x is Bernoulli P. b. So then we know that x takes the value 1 with probability p and 0 with probability 1 minus p. Okay. So then it's easy to see for any t in R, m sub x of t is just going to be expected value of e to the tx. So which is going to be equal to what? X takes value 1 and 0. When it takes 1, it takes 1 with probability p times e to the t. Then at 0, it's 1 minus p times e to the t times 0. So therefore, the moment generating function will just become what now? Let's say is equal to p times e to the t plus 1 minus p. So it's defined for all t now. So we can write down this m sub x is a function from the real line to the real line such that m sub x of t is just p times e to the t plus 1 minus p. That's the moment generating function for the Bernoulli random variable. So let me just give you an example of why it's called a motivation for why it's called moment generating function. Let's do a simple thing. So now let's go here. Let's compute the moments. So what are the moments of x? Let's see. So here is the moment generating function. Right? This is the moment generating function. Moment generating function. Right. What are the moments of x? Let's go back. Let's write moments of x. What moments of x will be? So e of x to the k. Right. So k positive, and e of x to the k is what then is just going to be equal to x takes value 1 with probability p and then 0 with probability 1 minus p. Right. So that's just it's always going to be 1 to the power k. So e of x to the k is always going to be p for a Bernoulli random. There's no difference here. But then Bernoulli random? But then one thing observe is that you can easily observe is that you understand how if I know m sub x of t, can I easily get e of x to the k? That's one thing to think about. We'll think about how to relate these things. So let's just put this question mark. How are these two related? Now let's do another next example. Let's do first one we did was Bernoulli. Next one let me do a continuous one. Let's see, let's say x is normal, let's say. So let's do normal. So let's say x is the next example we'll do is x is normal with mean mu and variance sigma squared. And let's try and calculate the moment generating function of that, right? So again, let's do same definition. So m sub x of t is going to be equal to expected value of e to the tx. That's just the definition, right? What's that going to be? That's going to be equal to the integral from minus to infinity e to the ty, and then the normal density is what? E to the minus y minus mu the whole squared divided by 2 sigma squared, the whole thing divided by root 2 pi times sigma dy. That's the definition of the normal density. And this is the expectation of e to the tx, where x is normal. Right? So now what's going to happen now? This is going to be equal to, let's see how to compute this integral now. So you have an exponent with ty and you have a square here, right? And you know the square is connected to the normal density. So that integrates out to 1. So what we do is you try and complete the square. That's all you do, right? So every time. So now what you do, think about this way. You think of this as, I'll do the computation, minus infinity, right? You have upstairs you have, let's write the whole thing down. The first term is e to the minus. So the top you have y squared, right? Plus 2 mu y, and then minus t times y. So I brought this t into this picture right here, right? And then the next thing I do is I just leave the mu squared up there, right? Mu squared. And the whole thing divided by 2 sigma squared. That's the top. And this whole exponent divided by root 2 pi times sigma dy. This is what I have. Very nice. So now what I will do is I will complete the square in a clever way. So what I'll do is I'll use this y and this mu plus t as one thing and then bring this outside the square. That's what I'm going to do, right? So this is what I'll do now next. So let's see. So now let's see if you agree with me on this. So we just copy this, I'll margin across, so let me put it across, put it down. Very nice. Let me bring it down to the margin of the page all the way down. That's very good. So now we go back up here. So now I have to complete the square. So how do I complete the square now? So what I do is I think of this person here as minus infinity to infinity. So what I'm going to do is I'm going to take, this is mu minus t, right, as the next term, right? So of course I made a small error. When I bring the t in here, I should bring a sigma squared as well. So let me bring that out. So I made a small error. Down. So I want to bring that t in, let me put it in blue. So I have to put a sigma squared in here, right? Otherwise it will not cancel. And a 2 also I have to put in. Otherwise it will not cancel with the bottom guy. Right? Very good. So what I'm going to do is I'm going to think of this person at the top as e to the, so moves across here. Go to this, I put this here, e to the minus. Inside here I'm going to think of this as y minus, right, y minus, so these are minus sign here, I made a mistake again, sorry about that, there's a minus sign, y minus of mu plus sigma squared t, right, b plus sigma squared t, the whole square. Okay, I'll think of it like this, the whole thing divided by 2 sigma squared. Okay, so now let's make this a little bit in blue so that it's clear. So it's blue. So this is what I want to write as the top denominator and dy. But of course and then whole divided by root 2 pi sigma. And why do I want to do this? If I do this like this, if I complete the square, then this looks like a normal density and I can integrate out to 1. But unfortunately what happens is the moment I do this, the above term is not going to be, has a little bit, only these two terms. If I expand the square here, I'll only have these 2 terms left, but I have to subtract the rest. So how do I subtract the rest? So this you can check. The above is just equal to, all I have to do is appropriately compensate. And what I have to compensate by? That's just mu times t, that'll be left, because the cross term is mu times t, plus I'll have 1/2 sigma squared t squared. That's all I have to do. Once I do that, then that's equal to the top term. There's nothing, it's a simple algebra. If I do this and add this to this, I'll get exactly this guy. That's what I did check. And now this density integrates out to 1. There's no problem, it's a normal density. So this whole thing is equal to e to the mu t plus 1/2 sigma squared t squared. So m sub x of t is exactly this for normal random variable, right? So x is normal with mean mu and variance sigma squared, then the normal density will have the homogeneity function is given by this particular quantity right here. Very nice. Now again, I again kept telling you this, and then in normal density we already know that the mean of x, we already know from before, the mean of x is just going to be equal to mu, and the variance of x, or second moment of x, is going to be equal to variance minus sigma squared plus mu squared. That's the second moment. It's also we know. So now again we have to see how the moments connect to the moment generating function, how this connection behaves. So let me think about it. So the next fact I'll state, this I'll state without a proof. It's a very nice fact about moment generating function and moments. So this tell you, once I know the moment generating function, it will tell you how to compute the moments of it. So now suppose, so this is the key fact, suppose let's say there is a delta positive such that, I like to write it in black, so I'll keep it in black, let's say. Suppose delta positive such that, sorry about this, mistakes happening, delta positive such that m sub x of t is finite for all t in minus delta to delta. Suppose I have a neighborhood around 0 for which this is. Then let's do a formal calculation. This is a fact. So you start with mx of t here, right? I differentiate it in t. Okay. So the derivative in t of mx of t is what now? So this is a formal calculation. You have to make it go slowly. It's expected value of e to the tx, right? So that's the same as, something you have to check, which is requires a little bit of proof. You can check that's the same as expected value of d by dt of e to the tx. So in this, the x is a constant, only t is changing. So same as expected value of t derivative of e to the tx is just e to the t times x. X times e to the tx. That's the first thing. Then one can just, little exercise you can do is that you can just check. So this is formal calculation. It's not rigorous always. You just make sure the proof is correct. So you can take the kth derivative. That will be the kth derivative here and the kth derivative here, and all I'll end up getting is a kth power here. So from this, and this is an interesting fact, one can immediately show, if I take the kth derivative of the moment generating function at 0, then I should just get expected value of x power k. Because I put k equal to 0 here, I just get t equal to 0, I get 1. So that's the key result. That is, all the moments of the random variable are just derivatives of the moment generating function. That's the immediate event you can get. So the moment you know how to compute mx of t, you can go and check that the kth derivative of the moment generating function at 0 is just going to be expected value of tx, x bar k. Sorry. This you can make rigorous, but I will not. You can look at the book. The book has this property. You can do. So now let's do an example, and then let's sort of illustrate this power of this moment generating function. So that connects up the moments and the moment generating function. So let me just so here let me just write this down in proper way. The kth derivative of the moment generating function at 0 is the same as the kth moment of x. Okay, that's what I'm trying to establish here. Very good. So now let's do a simple example to sort of see how to use this powerful idea. Let's do an example that we have not seen so far. Let's do the geometry random variable perhaps, and then that'll give you an idea how to sort of you can go back to the binomial and normal that I've done today and do the same calculation for yourself. But let me do this for this geometric one. So let's do an example. So let's say x is geometric with mean p. Or parameter p, let's say. Mean is 1 over p, we know that. But let's do mx of t. So what's mx of t going to be? Mx of t is going to be, again, expected value of e to the tx. Right? Okay, we don't know if it's finite or not. Let's investigate it slowly, okay? So formally speaking, it's the same as the sum from n equal to 1 to infinity, right, of e to the tx. And what is the probability of x e to the tn? X takes value n. We know probability of x equal to n is, in geometric cases, you have at the nth head you have a head, and you have failures till that time. So it's 1 minus p. So it's 1 minus p to the power n minus 1 times p. So this is going to be equal to what now? This is going to be equal to e to the t times 1 minus p to the power n minus 1 times p. Right? Very nice. So now how do I find this sum out? So now if you notice here, this 1 is separate, this p is separate. So I can pull those things out. So I'll just get this equal to p divided by 1 minus p. It's outside. It'll come outside. And inside I have n equal to 1 to infinity e to the t times 1 minus p to the power n. This is what I have. Now, of course, this geometric series will sum for what? When this will sum only when e to the t times 1 minus p is less than 1. Right? Otherwise, it will not sum up. So you have to be careful about that. So it will be equal to. So if e to the t times 1 minus p is less than 1 for such t, that is t has to be of that order. Right? So t can't be too large. then this will imply that mx of t is equal to p times 1 minus p, and this is going to be the first term is e to the t times 1 minus p, the whole thing divided by 1 minus e to the t times 1 minus p. So therefore for a geometric random variable, mx of t is just going to be p times e to the t divided by 1 minus e to the t times 1 minus p. So that's the moment generating function for geometric random variable for t in this range. For t small, so t less than, let's say e to the t is less than 1 by ln of 1 minus p. That very good. So now if you look at this, now it's an exercise one can do. I'll leave the exercise to check for you. If you take the first derivative of mx, so mx prime of t, if you do the derivative by product rule and so on and so forth, you will get p times e to the t divided by 1 minus p e to the t the whole square. That's what you will get. Okay, and you'll also get that the second derivative of t is going to be equal of mx is going to be equal to p times e to the t plus p times 1 minus p times e to the 2t, e to the 2t, and divided by 1 minus p e to the t the whole square. This calculus exercises, I'll let you check that. So from this you can easily check mx prime at 0 is going to be equal to, it's just going to be equal to p by p squared, which is just 1 by p, which we know from before. This is the same as ex. So verified the fact that the first moment is the first derivative at 0. Then the second derivative at 0, one can also check from the above. So the above will imply these two things. Is going to be put 0 here. What happens here? This is going to be p. This p plus 1 minus p, right? And the bottom is going to be just 1 minus p. It's just p squared. So what you're going to get is, you're going to get 2p minus p squared divided by p squared. And that's the same as by p, so it's p cubed. I'm sorry, I made a mistake here. This is p cubed. The derivative is p cubed here. Sorry. So I have p cubed here, and that will give you the answer is 2 over p squared minus 1 over p, and that's exactly second moment of John. That's exactly second moment from before. From before we know that. I'm putting the absolute value. From before we know that that's the same as equal to e of x squared. So verified in this example, I verified the fact that the geometric random variable, the moment generating function, if I differentiate it twice, I get the same moment at 0. Moment generating function 0, I get second moment. If I do it once, I get the first moment. You can check the same thing for normal and binomial as well. From this, you can differentiate this expression right here and see if you get the first moment and second moment. Similarly, for the Bernoulli, Bernoulli we already checked. It's correctly.